Hello everyone, and welcome to this video where we're going to be taking a look at modular engines, how to build them, how they work, how to make an engine management controller, and all that good stuff. So without further ado, let's begin. Now, as you see here, this is a small engine or a 1x1 cylinder engine, which is the smallest form of cylinders we have currently in the game. Of course, you use the cylinders, the manifolds, all kinds of pieces to make the engine. We're going to go through that in detail, and yes, I know I have a video about this, but this one is going to be a little more detailed. Inside the car, this is how it looks, and of course there's tons of applications you could use engines for. We're not going to get into that, but how to run the basic thing and how to make the engine management controller. Inside the component inventory, when you search modular, you get all this stuff. And as you can see, this is the 1x1 cylinder I was talking about. It is a single block. Then we have a 3x3 cylinder. And then of course the 5x5. Now in this video, we're going to be taking a look and using the small one. But of course, these bigger ones should be able to use the same microcontroller that you make. Now, if you use one of these bigger cylinders, you're going to use different type of belt drives. And you're going to use different type of crankshafts. Of course, unless you convert the crankshaft to a small one, which is possible as well. But we'll get into that in a second here. The first thing to do is what makes a component of a modular engine. This is a fully functional modular engine with 8 cylinders and a supercharger on the top. Now, supercharger is just a pump, and of course in the back here you have your power coming out. Now, how do you build this? If you don't know, you're about to learn. We can start by placing the first bit of the engine, which is going to be our crankshaft. That is the core of the engine. This is what the power goes down. So by placing this, this is kind of the framework. Now, off the actual framework or crankshaft, you attach your cylinders. So in this case, we'll make a 8-cylinder engine. I call it a V8 in this case, even though technically it's a flat 8. The point is, you just have to make sure that you align. See how it has this black, like kind of this part here, that has to connect to the crankshaft itself. So you place those in here. Of course, a V engine is like a V8 is in a V shape, but since you can't really do it here, or you can, but it's not really practical unless you want to use pivots and stuff. So this is what I call a V8, but flat 8, whatever, 8-cylinder engine. So now there's 8 cylinders and there is this crankshaft. Next, what you'll want to do on the very front is throw on your modular engine belt drive. And this is where you could run your accessories from. So that's an aux belt or accessory belt. And off that you can put your fluid pump. You can put all kinds of stuff. So we're going to start off by placing this fluid pump here. And as you will notice, it actually has to be clear from the back. So you may want to position that one on the top. This is what's going to circulate your fluid through the engine and cool it off. So we can start by putting that there. Then we have 2 other slots, or 3 other slots if we count the bottom. We'll put a starter on one of them. And then lastly, an alternator. Now, you don't have to put an alternator if you have a generator sitting on the actual path, but I always find these ones work pretty well, so they're good to have. Now that we've done that, you have to keep in mind 2 things. If you have a flat engine like this, but it's not an inline, so this would be an inline 4 with 4 cylinders, but if you have an engine like this, technically these here are all connected, and these here are all connected, but they're not connected to each other. So in this instant, you'd actually have to have on each bank of cylinders, left bank and right bank, you'd have to have their own fuel, their own exhaust, and their own air intake. But you don't have to do that if you connect them, and you can connect them with an engine manifold. So you do this, and you do this, and you put a straight piece, or you could even put an engine manifold T-piece and use it for something else after. But now they're connected. And of course, I sometimes just put for fun like this because I think they kind of look cool like an engine. But of course, this is unnecessary. If you have one, they are connected. So in this instance here, they end up being connected, so that's all you need. And then in this case, if you put your engine exhaust manifold, technically now that is exhaust on both banks of this engine. And of course, then you can apply the other things. So your engine is going to need your exhaust, it's going to need the air manifold, it's going to need fuel. So those are several important things, of course. We'll put the fuel over here. And then, in addition to that, you'll need to have the, if I find it here, this one, the coolant manifold. So coolant manifold is how your engine cools off. And you'll notice on this piece, there's actually two sort of fluid intakes, just like that. And if you go to your pump here, you see that there's two intakes or two ports. So what you do is you'd actually connect these two together like this, and you'd connect this together on the back. And now that is a closed system where it is using the coolant here from the engine, or this one, and pumping it using this pump here. Now, of course, if you don't want to put this pump here, you don't have to, but then you'll have to put another type of pump. So you could put an impeller pump or whatever, but you have to have a pump feeding this system. So this also would work. You have the ability to trial and test a lot of different combinations. You don't have to use a belt-driven fluid pump. So that is an option. Of course, there's other options. There's the impellers that you could also put. But we'll just stick to this. This is kind of the basic, and this is the way I tend to do it. Now here you have your fuel manifold. So at the fuel manifold, you will have to put a fuel tank. Of course, we're just building it in a very abstract kind of way. If you're putting this in your vehicle, you'll definitely want to adjust it and arrange it so it is kind of in a more cohesive state. However, in this case, something is fundamentally missing. What is missing? The radiator, of course. So the engine has to cool itself. Air-cooled doesn't really work in this game. Like if you did this, your coolant is being pushed through the engine, but it's not cooling down. So if you do put a radiator, that will substantially help your engine cool down. Now, just for the purpose of this video, I'm going to kind of put it laying down on the ground here. But of course, there are many different arrangements you can place this in. And what you'll need to focus on is having your system go through these various ports and come out and be fed through this. So in this case, what we can do is place one pipe there, and then we'll place the other pipe on the other side here and have everything fully connected. And in this case now, what will happen is you will be pumping out of your engine here. This is coolant B, but it doesn't really matter. Point is, it flows through here into the radiator, then out of the radiator into the pump, and then it goes to the pump and it makes this circle and it goes through that radiator. So that's the key here. That is a coolant system now. For your exhaust system, what you'll want to maybe put in addition to this, and what I'll do is I'll color code this one a different color, we'll make it orange, is in addition to having this port, you'll probably want to put a catalytic converter. Now the catalytic converter, if you put it this way, just make sure it is exhaust out, because they are not unidirectional. If you place it this way, that's exhaust in, does not work. So if it's facing exhaust out, and then if you put the exhaust on the top here, but you could also use a regular port, you could use another type of port. So there's various different ways. You could use a fluid port too. Point is, that is an exhaust system. That's all you need. The exhaust system is the easiest system. If you have a catalytic converter, it's going to reduce the amount of smoke that goes through that system. For the gas tank, and I'm going to color code that one green, you have your fuel manifold, and then it goes into a fuel tank. Of course, your fuel tank is always useful to have a hose on the end of it so you could refill it. But for the purposes of this video, I mean, that's really not necessary. We're just doing a sample engine. Sometimes also I saw the developers on their test engines place a gas relief valve. I've not personally found that it really impedes my creations now if there doesn't have the gas relief valve, but the point is this is what you need for your fuel tank. Then for the air, this case you also can just have a port. You could have a port, or you can have any type of air intake, air filter, there's air ram, there's all kinds of different stuff. This one actually performs better at higher speeds, so you're kind of at the freedom of putting whatever you want. That's also where you'd put a supercharger if you want. And I know there's been tons of comments on my supercharger video saying that's not really how it should work, because what I just do is this. I simply put a fluid in and a supercharger, and what will happen is this will pump, it'll fill this area up until this can't even suck in any more air, and then it sucks in air, and then this pumps. It's not like a consistently flowing system. With the variable flow valve, you should be able to regulate the amount of air going through your supercharger and control it a little bit better, but I don't find that it suffers the system. Maybe it doesn't work as effective, but it still adds power even in the most blunt way possible. Anyways, these are the various systems that you have in your engine, and I will color the manifold red. So in this case now, and of course if you're not using this one here, you don't need to have this as a T-pipe. You can just have it as a simple straight manifold connecting that too. That just gives you the flexibility in the case you have an engine like this, where you want to make it as compact as possible, and then you could utilize those manifolds in other ways. But pretty much there is our modular engine. You do a very similar style with the 3x3 or the 5x5. Just to quickly show you here, if you start with your 3x3 crankshaft, you put 2 of them. We can make this a 2-cylinder engine. So you align this, you just have to make sure that these connectors are all aligned properly, like that. And then on the back of this, you can then convert it into a smaller one, so 3 to a 1. Of course, also you have this flat one here, which works too, if you want. But the point is, and this one converts them actually into using the smaller style manifolds, if you want to make connections for multiple banks. But again, this converter you throw on the end of this, and then you could notice now they are the same, where you can now just put that single clutch unit coming out the back here and coming out the back here. So you have to have the clutch in order for the power to come out, and then this is where you could put your wheels, your generator, whatever. That's now RPS. In the case of a 3x3 or a 5x5, you'll definitely want to have more starters because your engine will struggle to start. So you want to put like starters, or even have, like I found that 3 work well for a 3x3 depending on the size of the cylinders. Or on this side you can also put a electric motor that will kick on with the electric power and kind of jump start the engine. But those are kind of the configurations that you'll want to have when you have a modular engine, so you may need a little bit longer of a startup time with them. Also, I don't really build with flywheels. I find that they're not really needed for my application, so I'm not going to really talk about them in this video, but I will get you a working modular engine by the end. So this is what we have here. Now in the previous video, I just told you to connect this to Mr. NJ's microcontroller, but in this case, we are actually going to make this work ourselves. For that, we will start with a couple things. We are going to put a toggle button, which will also, or could be a key button. And we will put a throttle. And again, the throttle could also just be your seat itself, but in this case, we'll just stick with this. Then you need to have your battery, and you'll want to connect your battery to the components of your engine, of course, and to your key and throttle. Now what you'll also need to do is go into your data here and do a couple things. So when you look at this, you see that there's some data nodes. One that I forget sometimes that I strongly encourage you to put is your alternator and your fluid pump pressure is just easiest if you attach it to one of your RPS on your engine. That's pretty much going to ensure that they're working if your engine's working. Of course, you also could put a constant number and just make it constant 1. That is the same thing. So in this case, you could just put constant 1. One thing to watch out for, and one thing that I kind of learned the hard way, is I used to just connect my clutch here to my RPS. I used to connect that also to the fluid and to the alternator, but I found that if I brake really hard, my engine will stall, and I have a motor on this side of the configuration, like somewhere here, you know, I have my wheels and whatnot, but I also have an electric motor to sort of serve as a jump start. But guess what? That motor does not work now because you closed this clutch. This clutch is related to your RPS. Your RPS dipped down to 0 because you stalled your car, and now this is struggling and forcing power into your system to jump start it. But guess what? It's not happening because this is closed off. So I learned the hard way, and I have to actually go and fix this on all my creations. So I prefer to just keep this open on a constant number. That just kind of helps my system, because what I do is I kind of do the old school way of having an actual clutch down the stream here somewhere. So for me, it doesn't really matter. That clutch can just fully be on for all I care. So in this system, this is always on, and this can jump start it as needed, and then this is my main clutch. And what I also do then is on this stream here is if I want to have any alternators or generators, I put them here. Alternator, generator, I call that the same thing. They produce power. So I put them on that same path, and then they're always working regardless of if your engine and your wheels down here are spinning. But for this exercise, that doesn't matter. Just a little tidbit for you there. So I would put at least this on a 1, or put all this stuff on a 1. Now maybe it's not bad to leave these guys here attached to the RPS, for the reason that when you're starting the engine, you're not putting power into these things. They're not sapping power until you've built up an RPS, and at that point these guys can run. So this is maybe the configuration that I'd recommend for you. The other ones we will deal with later. So we need to put an empty microcontroller, and then we'll start to populate it. Now there are lots of different ways to make these microcontrollers, and I'm not claiming this is the best one, but I'm claiming this is an option and maybe an easy sort of way that you can program your own engine microcontroller. But of course, there are units out there that have been tested and developed and function very well, so don't get upset if this is too basic, or if you wanted something super super intense. This is just a basic one to get your engine up and running. So what we'll need now inside our engine ECU, or engine control module, ECM if it's a car, we'll need to put a couple of things. We'll need to put our input. This is our key. This is our actual engine starter, to turn on the engine. And on that note, we'll need the actual starter for the engine. We'll put that out on another node. Then, in addition to that, you'll need a couple of numbers coming out. Primarily, you will need your fuel, and you will need another output to go to the air. So this is the air intake, and this is the fuel module. So these will actually be attached to the fuel manifold here, and this will be attached to the air manifold right here. Now, in addition to that, we need a couple of other things. We'll need to put another one for the throttle, and that is going to be an input, and then attach the throttle to here, and attach the starter to the starter, attach the key to the actual key. Now looking at that, that seems to be fairly okay. Another thing with the key should activate your radiator. So if the key's on, engine's on, the radiator is always spinning. Yeah, it's wasting a little power, but your alternator should pick up on that slack. Inside the microcontroller, we can arrange these things in a way that is logical, so just like this. There are a couple other nodes that we can add. One of them will be a number input for the battery, and then another one will be composite, and I'll explain how that works in a second. and that's going to be attached to the cylinder. Now if we arrange them here like this, the composite one is going to require a composite read where you pull values out of it. Now what do each one of these channels mean, might you ask? There's 3 of them, so 1, 2, and 3. And if you update your microcontroller here and go into the cylinder, you could see that it says air volume is 1, fuel volume is 2, and temperature is 3. So those data points you can connect to this microcontroller. Of course, we didn't expand it out, so your next logical steps to grow it out like that. So this way you can attach this to any one of your cylinders, and of course you can attach your battery to your battery. Earlier I was talking about making your, boosting your motor if it's about to stall. So I always like to put a number output for my electric motor. And that's pretty much just gonna make your engine stall less or prevent it from stalling. So we can attach that here to this motor. And now we're kind of in shape to start programming this. The first thing you'll need when you turn the key is for your starter to work. So you're going to turn your key, and pretty much what you're going to want is a capacitor, and that capacitor is going to not charge uptime, but it's going to discharge for, let's say, 2 seconds. However, if you attach this directly to the capacitor, it may keep sort of recharging it or restarting it because you're constantly applying. So it is always good to make this into a push. So it'll be going from toggle to push. So it's a pulse, and it sends a pulse into this capacitor. There is no charge up time, and there's a 2-second discharge time. So that's the first thing you'll want when you turn the key, for that to sort of start up. Next, then, you have your throttle. Now your throttle is defined by your lever or your seat. If this were not a modular engine where you didn't have an air intake and a fuel manifold, you'd be able to just put your throttle directly to the throttle of your engine. Now, if you do that here, like this, you're going to have a lot of problems. So the way that real life engines work is the ratio of fuel and the ratio of air is your air-fuel ratio, and that sets kind of how the engine works. Now, if it runs lean or it runs rich, that really depends on what you set it here. If it runs lean, that means it's fuel starved. If you have too much gasoline in the air mixture, then it's what's called rich, and you have too much gasoline. Either of these instances are not good. In air-fuel ratio, stoichiometric air-fuel ratio of around 14:1, which means 14 grams of air are required for every 1 gram of fuel, is sort of the ideal when it comes to this type of stuff. The ideal would be that the gasoline is fully burned with no excess air in the system. So you have to have the perfect amount of air, the perfect amount of fuel, and that combination will result in a smooth running engine. With that in mind, what we're going to do for now, and just to see how it sort of works, is we're going to put a function, just a simple fx function, and say that this will be going to our fuel, and it'll be half, so 0.5 times x, or x divided by 2. But in this case, now we have less fuel entering our engine for the air. Now it's not a 14 ratio, but we'll see how this sort of plays out. So with this in mind here, we don't even have to connect any of this other stuff. We should be able to at least start our engine to a basic level. We've spawned it up, and if you start it, your throttle is at 0, keep in mind. So let's try throttle of around 30. And there you have it. Your engine is on. If we go into here, we could see our air-fuel ratio is 13.9, so that's not awful. Not awful at all. And it's working pretty good. Now if we turn it up, of course that's way too high of RPS and it's going to overheat like crazy. But if you slow it down a little bit, around 20 is where these engines are really happy. And it seems to be going. Now, if we turn this off, this will still kind of continue, because remember, this button only really started our sequence by causing the starter to go, and this won't actually turn off our engine. So right now this controller doesn't fully function, but we got it up to a certain point. So what you'll want to do is have your key function here. It has to change your throttle, and what we need to do is introduce a numerical switch box, attach it to both of these nodes here, and attach it to the on position with the key. So when the key is turned, we have whatever value we're putting through the throttle. When the key's turned off, there is no longer anything going through the throttle, and these will both be 0 values, and the engine will stall out or turn off. So that's sort of how this very first basic part of the equation works. One thing that intrigued me was the fact that we didn't actually put a 14:1 ratio in the air intake and the fuel manifold. And the reason for that is because in the game here, these different parts or different units will actually allow just allow fuel in. You're really controlling the throttle. You're not controlling that ratio, right? So keep that in mind. So we had a ratio of 13.9, which is pretty good. It's honestly not awful, but we can actually fine tune it. Though, if you are happy with this microcontroller as a very basic one with a key input, a starter, a throttle, air intake, and fuel manifold, you are good to go. This is all you need, and you can get a motor running and working. Remember how we mentioned this cylinder information? Well, this stuff can actually get us data of what we need for our engine. Remember, 3 is temperature, but 1 and 2 are the fuel and air. So what you can actually do here is have a division dividing the air over fuel. So 1 divided by node 2. So if we go into here, we can actually take this division, so 1 divided by 2, and that can be displayed as a number tooltip. So in this case, now that number will be displayed, and we're going to know sort of where we're at. Now we could take this one step further even and develop a system that will actually increase or decrease this ratio until we have a happy level of air-fuel ratio. If you've been following along from the beginning, you may have noticed that I have these things here when you select my microcontroller, yet they're not visible, and that's because I've actually been referring to my previous arrangements. But if I delete all that and make the actual microcontroller the way it is, there is nothing here, so don't be confused and think that you missed a step. There are no properties that we could select, but we are about to do that now. So what we have here is this air-fuel ratio property value. What we can do is add a slider now, and on that slider we can put air-fuel ratio, and let's start off with 14 and end up with 15, and you can have the rounding to be 0.1, and we can have that value of 14.7. that is kind of like the sweet spot for air-fuel ratios. Of course, you're free to make this range different, maybe 13 and 16 if you want, and you can kind of play around with it. So with that done now, the next step is to make sure that this air-fuel ratio that we set on the slider will correspond with an air-fuel ratio in the actual engine. To do that, we will want to use this air-fuel ratio that we have coming out of our cylinder composites, and depending on how they compare with this value here that we've set it to, it will adjust the fuel manifold's equation. So this equation here will be made to be able to be adjusted. So I'm just going to move these up a little bit, and we're going to start off. So we're going to need to have a less than and greater than function, and we'll have to have a up and down counter. The air-fuel ratio that we connect with this property slider, we're going to put on the bottom of these functions, so on the B slot, and then the actual data coming out of the cylinder, the division of these two things. So the actual air-fuel ratio we're going to put on the top. And that's going to cause a comparison of the actual air-fuel ratio versus our set air-fuel ratio. So in the case of you having an air-fuel ratio coming out of your actual engine that is less than what you're comparing with your value here, you're going to want to have this turn down the value that goes to your fuel manifold. And likewise, the comparison, your air-fuel ratio comparison, if the actual cylinder is greater than what you set on the slider, you're going to want that to increase your fuel manifold, or how much fuel you get in, and it will reduce the amount of air. It's going to bring down the ratio. So these actually could be flipped like this, so they're sequential in that nature. But this is now in essence what you'll use, and see how it forgoes this 0.5 here. So this 0.5 value is now able to be removed. We don't need this anymore, but we have to adjust this up-down counter to make up for that. So what we're going to do is put a value of 0.00005. We're going to make the reset value 0.5, like what we had. We're going to turn the clamp on. We're going to make it a minimum of 0.2 and a maximum of 0.8. So you see that it starts off on that 0.5 value that we previously had, and it works its way up or down based on what we set on this property slider. Now, one thing to remember is having removed that function here means that when the engine is off, it still is working this function. It's still moving this up and down. So actually what we're going to do is move this back a little bit and add two AND functions here and here, and we'll connect them to these things. So we'll put the B on there, we'll remove it from here, and this one will attach to this one will attach to this, and what we do is on the AND function now, you'll make sure that the key is turned. So the engine is on and the air-fuel ratio is less or greater, and then this happens. Now we don't have to add anything to the reset value. Really, the engine can tune itself as it turns on and off, but it's not a bad idea also to just reset it every time. So if the key is not turned, it resets to that 0.5 value. And the last thing that I'll do here, and you see that we have this numerical switch box, is we can add a numerical switch box coming out of this, attached to the key, and if the key is turned, the fuel manifold is on. If it's turned off, it's 0, meaning the fuel manifold will no longer want to suck fuel in, and the engine will stall out in that case, just like we had. So this arrangement now works, or should work, but this is sort of the way that we're going to be tuning up or down our engine based on the air-fuel ratio that we set. Something you might want to do with your throttle is have a minimum throttle as well, meaning it is always 0.2 at the least, so you're not stalling out your engine by turning it on and having the throttle set to 0. So this just prevents the engine from being kind of stalling, but this is not what you do in a car. In a car, you want it to run, you'll set it a little differently. This is something you'd maybe do in a generator situation, or something that's just kind of sitting there. So if you turn it on, your minimum throttle is just 0.2. So we'll spawn this in and go take a look here. So even 0.2 is too little. And you can see now it's working its way up, the air-fuel ratio, but it's also it's getting too slow to that 14. It's moving up. So it wants to stall itself out, so it seems that this value here isn't really coming in at the right speed. Let's see what happens when it hits that 14. So now it's actually bouncing around at that 14.7 mark, but it took a while to get there. And look at that, if we turn down our throttle, this actually drops very fast. So we have to revise this because something here doesn't quite work the way it should. So that air-fuel ratio is fully dependent on the throttle right now. So if we dig into our actual microcontroller here, you'd see that the throttle, which goes into here, goes directly to our air intake, whereas the fuel manifold one will go through this whole process. So we actually do end up with a fundamental difference of what ends up happening, because of the value isn't being compared with the throttle, it's being compared with the air-fuel ratio in this instance. So only when you are at a full open throttle or a 1 throttle does this 0.5 even come into play. So something has to be added here. And what that is an actual multiplication or function to take your actual throttle, multiply it now by this value here. And that's what goes into the fuel manifold. So don't forget that step. You can't end up doing a pure comparison of a full open throttle. You have to still apply your actual throttle to this value that's going in and out of this up and down counter. And that's what's going to set what goes into your fuel manifold. So you'll see now if we spawn this in, you're going to end up with a ratio that's, even at a throttle of 0.2, it's bouncing around that 14.7 mark. And as we turn it up, it's still bouncing around that 14.7 mark. So in this instant, you see that it will live adjust itself based on whatever your throttle is. Now, the number is bouncing around quite substantially, so we could slow it down again by adding another 0 here. And at this point, even you could increase these values, but that shouldn't change anything because you're still comparing it to your set throttle versus an arbitrary maximum throttle value. So if I turn the key here at 20% throttle, the engine's not stalled out, it's building RPS, and it's now coming to that 14.7 mark. And you could see that if you go here, you could see we have a quite low efficiency, which is fine. And as you turn it up, it goes quite low. So that 14.7 may not be the best setting in Stormworks. So we could try out now, and if we put it to 100%, it goes to 40%. So we could check out different values, and this is really where you testing different values in Stormworks with your air-fuel ratio is kind of fun. So I'm not going to spoil it for you, but let's just try 14.4. We're getting a little better efficiency, so we're no longer 39. You can see that we are at 41. And if you turn down the throttle, it's actually increasing in efficiency. So you can play around with that. You see that the air-fuel ratio here that's showing on when you point at the cylinder is the same as what we're showing when we're looking at this ECM. So there you have it. Now you've succeeded in adding an active air-fuel ratio management system based on the output of your cylinder and the data that you have collected into that. At this point, you pretty much have a working, call it generator, so you could then put a large generator at the end of this or something. It's possible to convert this into a car application, but it's not quite there yet. And I will showcase that in a different video, how to make this ready for an actual vehicle engine with an actual clutch here at the end. But this is a system that you just crank on and it runs pretty much. So there's no setting of like the clutch, the power going to the wheels will be instantaneous. So it's not really a good vehicle microcontroller. But you can see that even with this generator there now, it's pushing through. It has a decent efficiency, and it's running the medium generator here now. So this is, let's say, like a generator style motor, And there's a couple of safety features that we could build in here that will be utilizing the rest of these logic nodes that we have. So we've added electric motor that we never touched, and we have battery. If it notices that the battery is too low, you could force the throttle to increase a little bit and create more power through the alternator or generators. And here we have the electric motor, which is quite easy to do. So what that's going to be reading, and that we could apply it quite easily here, is if we have our key on, and if we have our RPS struggling, you'll actually use the electric motors to turn up or boost the amount of to kind of jump start it almost. So we'll need to look at a couple of our nodes here for that. First, we'll have to add an RPS function here because currently there is no RPS gauge. So that'll be a number input. And if we spawn it in here, that's just a very simple one to attach to any of your crankshafts. And then if we go in here, you take that RPS value and say that if your RPS is less than a certain value, and if your engine is on or your key is on, then you'll want to put it into a numerical switch box that will force the first value on, which will be a constant number. And I'll probably just put a 1, to be honest. Full throttle, you're trying to jump start it. Now, what's important here is this RPS is less than. Generally, in this game, if your RPS is less than, let's say 4, I'd just say 4 from experience, it's on the path to stalling. Like, yes, you can run an engine less than 4, but it will be on the verge. So if it's less than 0.4 here, we can make this sequence happen. And it's quite easy. We just have to make sure everything's connected. So our electric motor is connected there. You'll notice that with this larger generator, your engine almost struggles a little bit to turn on. And it is an 8-cylinder, but it's still a decently large generator, so it will sort of struggle a little. And you may find that at 20% throttle, it will ride at like 5 RPS. Like, it'll be on that verge of shutting off. So we'll see how this electric boost or jump start helps us here. So I will turn the throttle up a little higher, so you could see how it pushed the engine to start quicker. And if I turn this throttle lever down and turn this on, you could see that that motor was kind of jumping. It's like pushing one because that RPS keeps dropping lower than 4. So this setup, you can't really run at 20%. But you can see now it's running at around 6, and it is not stalling. So this is actually a functional system right now, and you can turn it up. But again, anywhere in that like less than 10 RPS range is really not too like, it's quite silent, and it's like, which is good, it's quiet, but it's also very low RPS. But anyways, where we put it at 4, I think, is a decent area. Obviously, if you stall it, you stall it. You can adjust the values. Of course, these are just sort of my ideas of what you can do. Everything here is free for you to change and fix as ever you find necessary. So I'm just giving you the framework to creating a motor here, and you can kind of use it as you see fit. Now, another thing that is useful to have in your microcontroller is one thing we haven't touched on, which is number 3, our engine temperature. So engine temperature can cause your engine to start on fire. If you have a too high of a temperature, usually if it's more than 100 degrees or 110, 20 degrees, it can start on fire. So that is somewhere where I'd actually put a threshold gate and say that if this is between, let's say, 100, and you could even go like 999, doesn't really matter. But then you may want to add this part, and then here you'll set a property toggle. So you could say overheating shutoff. overheating shutoff. So if it's more than, let's even go higher. Let's go 110. And if we have the overheating shutoff on, then you will want it to turn off. And that turn off function is the same thing as our key being off. So if we follow all of these sort of logical areas here, you see that it applies there and there. So what we could do is have this here and then add a function and then this one now you'll want to connect to everywhere where the actual engine or key start is connected. So there is quite a lot of them. You have to kind of go through and add each one. But now if the engine or key is turned and if this function, so if right now if this is toggled on and if we're above this temperature, then something was going to happen. But it's an and function here, so I will say not this. So in this case, if the key's on and we've not gone through this sequence, then you can run the engine properly. If we have overheated the engine and this toggle shutoff property is on, you won't even be able to start the engine. It will prevent even the starter from turning. It'll fully be like you've turned it off, and it will not allow you to turn it off until your temperature drops a little less. Another good safety feature is a throttle reduction. So we could have this between 90 and 999, whatever, and call this overheating throttle down. And if this value is on, we're going to make the throttle, which we set here, turn down a little bit. And that's an easier way to do it. You just put a numerical switch box. So if this function is on, and if we're between this, we don't even have to have this not here. We just have it if it's overheating, and if we're between these values, then it will switch. So when it's off, we have our normal throttle, and we have to just make sure to fully connect it. And if this sequence happens, then we go through the on value, which will just be like a function, an fx, and we just make it, let's say 80% throttle. So 0.8x multiplied by x. So in this case now, we've just taken our throttle and reduced it to 80%. If that doesn't help our situation, then if it hits 110, it's going to turn off fully. Now the reason why you have, these are right now thresholds, but you could make them as functions comparatively, like lower if it's within range, and then you can set the actual number. But in this case, you just have to go into the microcontroller and adjust these, which is fine. I don't really mind. But you'll see now, you have the option to turn on or off this, or you could turn them off, both off, or whatever. So it kind of gives you that flexibility and the ability to set a little bit of a safety factor into your engine and prevent them from exploding if it gets too hot. If it is a generator, you may want to have the battery be able to actually start the generator if the battery drops low enough. But in the case of a car engine, if the battery is low, you'll just want the engine to maybe turn up the throttle a little bit. So if we have the battery less than a value that we set here on the property slider, so we could say generator mode activated, battery level, and it'll be between 0.2 and 1 with the rounding of 0.1, and we'll have the value starting at, let's say, 0.6. So if the battery drops less than 60%, then we'll want it to be in a pulse, or we'll want it to send a pulse into an SR latch. And the reason why I want to do this is because now I want this battery to activate a mode that will, in essence, turn up our throttle until a time when we can reset this. So when it'll be reset, it'll use a threshold gate, and it'll reset it when it's 100. So when the battery hits 100, it will reset this SR latch. Now this little function will be able to turn up our throttle. So what we can do is add that into our path for the throttle. Now, one thing that we have to note is because we did also turn down the throttle when we have a overheating engine situation, so this, I don't want to bother that. Meaning, if we're overheating and our battery's low, I don't want the generator mode on. I want still the engine to be detuned. So we're not going to put it downstream of this numerical junction. Instead, we're going to add it in here. So if we're not in overheating mode, then we can actually play with having this generator mode. So as long as we're not overheating. So what I'm going to do is now splice in a numerical junction into this path, which is the off path of the overheating mode. So if it is off, then it goes where we were going anyways. If our battery is less than this and we have our generator mode on, etc., then this becomes on. So we could actually drag this up to here and we'll place it and connect it to this. Now in this case, again, so if your battery's lower or dropped, then you send an SR latch pulse through here and you'll need the on value. The on value now will just be an addition to your throttle. So your throttle is here. We could have a simple addition. It'll be the throttle plus a value of our choosing for the generator mode. So in that case, we could put another property slider and I could just say generator mode throttle increase. You won't want to go much higher than 30%, I would say. So personally, I would leave it between 0.1. We could even put 0 if you want to turn off this generator mode thing. So it'll be 0 and let's say 0.3. With a rounding of 0.1, that's fine, and we could have it a value of 0.2. So in this case, if we have low battery, it will be added to our existing throttle and go through here. Of course, if we have a overheating situation, that won't even matter because we don't want the generator mode on if our engine is overheating. So we can go ahead and throw that in here. Make sure that everything's connected. Of course, it still is. Now, one thing that we have to note is if we turn this battery down to activate our generator mode, this engine will not start because it has this massive generator here. It's not going to have enough juice to crank it over. So I'm just going to remove this generator and put a small generator on there just so our engine can crank over. And then we'll actually see that the overheating mode will not be on, but what will be on is the generator mode. So if we go here, we can set this to 20%. And if I look at the throttle in the fuel, it's 20. Here it's 40. So it added 20%, or it added 20 extra throttle. So this is 0.2. So I'd think adding 0.2 is too much. Like that engine, even at low, is quite active with a very high RPS in this case, but also that is because we put a small generator. If I put the larger generator, the engine wouldn't run with that high RPS, but you get the gist. It's sort of a way to activate the engine, turn it up a little bit, but maybe I'd rather put this to be maybe 0.1. So just increases it ever so subtly. I think even in my engine microcontroller, I use a much less value. Like if we go here into my generator mode, it increases it by, if I keep looking here, RPS increase. Yeah, so the RPS increases by 2. So whatever the RPS is, it only just slightly increases it. Anyways, this is now a working microcontroller that you could use for generators, cars, all kinds of things. I will go into detail and make another video on how to make an actual car sort of super microcontroller that has the clutch built in, the brakes, the steering, everything in one smooth spot, and it's going to be using this microcontroller as the fundamental basis. So for that video, you'll have to have this as a starting point, and then you could follow along for the next part and get the rest of it going. So thank you all for watching, stay tuned for more, and as always, happy Stormworksing everyone.